Hi, everyone. Thank you very much for a very kind invitation. It's my great pleasure to be here. And I would like to thank everyone at KQC for having me for this wonderful event. I'm not sure what happened to my slide. The title is not showing up, but supposed to be quantum machine learning, opportunities and challenges. So I wanted to give a little bit of perspective on this quantum machine learning, and also at the same time, I'd like to give a little bit of taste on what my group does in Yonsei University. Okay, and again, so I'm from Yonsei University. I'm in the Department of Applied Statistics and Statistics in Data Science. And sorry that I have written my name in Korean, but I'm Kyungdeock. Okay, let me see. All right, so I see that some things are broken, but I hope it doesn't cause any much problem. So I basically copied and pasted my research group webpage. So we are QDNA, and it has nothing to do with biology. It's quantum data science and AI. And we have 6 students and 2 researchers. So our group is growing, and I'm really happy for that. I'm really thankful for that. Just to quickly tell you what we do. So as the name for our research group indicates, we try to harness quantum information theory to solve various challenges in data science and AI, and we also we are hoping to develop some industrial applications of quantum computing in the near future. And also there is very important topic about how we deal with noise and imperfections in quantum computing, and we try to develop statistical and machine learning methods, that fight noise and imperfections in quantum information processing tasks. And if you're interested, you could also visit our website. All right. So where does quantum machine learning started from? I see that the slide is a bit broken. I don't know why, but okay. Anyway, so this paper, well, this paper came out in 2009. Of course, the people talked about quantum machine learning even before that, but this is a paper that really, brought a lot of excitement to the community. And if you look at this paper, what this paper says is that it says that if we use quantum computer, we can solve these linear systems of equations exponentially faster than with classical computer. In other words, we can do matrix inversion exponentially faster on a quantum computer than on a classical computer. And this brought a lot of excitement to quantum algorithm and also like machine learning community, because matrix inversion, it's something that happens, that appears quite a lot in data analysis in general. Like for example, like when we consider very basic like data analysis technique like linear regression, we have to do a matrix inversion on like a large covariance matrix. So this is quite common thing to do in data analysis, and this tells us that we can solve this basic subroutine on a quantum computer a lot better than on a classical computer. And after this paper came out, many people they went on and they used this technique as a subroutine to use for machine learning. But then that's all great, but in fact, this matrix inversion algorithm, which we also call HHL algorithm, named after the authors of the paper, is actually a lot more, it's slightly more difficult than implementing the Shor's algorithm for factoring. Okay. In other words, even though this is a great algorithm, we have no idea when we'll have a quantum computer that will allow us to implement such an algorithm. Okay. So again, like Shor's algorithm will be easier to implement on a quantum computer than this matrix inversion algorithm. So this is like a long-term perspective. Then we now need to consider then if we cannot use this wonderful algorithm for quantum machine learning in the near future, then what can we do in the near term? Well, people have worked quite hard on this topic, and there are a number of candidates. Okay, so in the near term, for near-term quantum machine learning, so I'm just going to list out a couple of topics. Like there's a kernel method. There's also like variational, in other words, trainable quantum circuits. There's like non-adiabatic quantum annealing, and usually people don't bring this up. They don't mention this. They just say quantum annealing. But it's very important to note that we're not doing adiabatic quantum computing. So it's a non-adiabatic quantum annealing. And they're also like quantum-inspired classical algorithms. And this is quite interesting because these algorithms, they are, like as the name indicates, these algorithms are inspired by like quantum mechanical principles, but we don't necessarily require quantum hardware. Okay, so we design algorithms based on quantum mechanics, but we run them on a classical hardware. And that could still be beneficial if our goal is not so much about reducing the runtime, but we care more about accuracies. Okay, and I also wanted to quickly mention that in conventional quantum algorithms analysis, usually like all of these like computational complexity analyses are done in the language of like big O notation, like it's done in the asymptotic limit. But in practice, the constant factor hidden in this asymptotic analysis is also very important. So in the near future, in the near term, for the near-term quantum machine learning, we also need to consider, okay, maybe the quantum computer does not guarantee exponential speed up, or maybe even polynomial speed up, but maybe there is a constant factor improvement which we care about. All right, so from now on, so there are basically these 4 categories under near-term quantum machine learning, but I'm going to focus on these variational quantum circuits, okay? All right, okay, this is really broken badly. Okay, but let me try to, so it was a really bad idea to use equations for this talk. But basic idea of these variational quantum circuits is to train a quantum circuit. First, parameterize quantum circuit, and then train such a quantum circuit to solve optimization problem. And then because like optimization appears in so many applications such as machine learning, chemistry, like finance, in so many domains, if we can somehow utilize this idea, then we can find many applications of quantum computing. But the key idea is let's say we want to solve some optimization problem. First of all, we need to define a loss function. And here, loss function is defined as some sort of quantity that we measure from a quantum circuit. So on the very left-hand side, I drew some abstract quantum circuit. And after we perform some measurement, because the probabilistic nature of quantum computing, we measure some expectation value. And that expectation value could be used to construct a loss function. And because quantum circuit is, we design quantum circuit in a way that it's hard to simulate classically, we can say that such a loss function that we construct out of quantum circuit will be very hard to compute classically. Okay, so that's all great, but now we need to, once we define the loss function, we need some algorithmic means to reduce it, right? We need a way to kind of find the minimizer of such a loss function. And we know that the gradient-based optimization is quite useful for that. In other words, we want to be able to compute the gradient of such loss function with respect to the set of parameters. And the good news is, so basically what this broken equation tells us is that in fact we can compute the gradient of the loss function with respect to the set of parameters using a quantum computer itself. Okay, so that's a really important point. So we can not only compute the loss function using a quantum computer, but we can also compute the gradient of the loss function using a quantum computer. Okay. In other words, we basically, we can from end to end, we can perform gradient-based optimization using a quantum computer. And this is really great news, because then we can just rely on a quantum computer for running over this optimization process, which could potentially be applied to many applications. Okay, but then, okay, so this is good. Analytical gradient can be calculated. Actually, we need two quantum circuit measurements. Okay, that's great. But in this quantum-based optimization or quantum algorithms, what's known as expressibility is very important. This is a very complicated concept, but in short, basically we want to design our circuit and we want to parameterize our unitary gate so that with using the set of parameters, we want to be able to generate as many quantum states as possible. So we want to cover as much space on the Hilbert space as possible. So expressibility is quite important in this context. But it is theoretically shown. In fact, it is theoretically shown by those people who first suggested this variation of quantum circuit. They showed that there is this problem of what's called the Barron plateau. This means that if we want to really go for expressibility, then this gradient quantity that we compute is computed out of expectation value, meaning that we have to repeat the same circuit over and over many times to compute the expectation value. But what this says is that if we want to go for expressibility, then such expectation value will vanish to zero exponentially with respect to the number of qubits. Okay? So this is very similar, even though at the fundamental level this is slightly different, but we could compare this to the vanishing gradient effect when we train deep learning. So this was a bad news, right? Because we can compute the gradient using a quantum circuit, but the gradient will become exponentially small with respect to the number of qubits, meaning that the number of repetitions that we need to perform in order to estimate the expectation value will grow exponentially with the number of qubits. Okay? So, perhaps we might have to sacrifice a little bit of expressibility, which is very similar to putting a prior distribution to our problem, and that could vaguely correspond to designing these variational quantum circuits with some specific structures to kind of give up on expressibility to avoid Barron plateau effect. So once this Barron plateau effect was suggested in 2019, ever since that, basically, most of the quantum machine learning research based on variational quantum circuit is about how we avoid Barron plateau effect while maintaining the quantum advantage. It was found that Barron plateau effect could be avoided by using such structure. So I'm not going to go into all the details about this structure, but the basic idea is that we start from some number of qubits, and then so these blue and red areas, so blue rectangle and red circle, those are the gates that we parameterize with the model parameter. But basic idea is that we start from some number of qubits, here for example 8 qubits, and progressively we throw away half the qubits. Okay, so we progressively reduce the number of qubits all the way down to 1. But once we perform measurement on the very last qubit, we either obtain 0 or 1. So perhaps we can use that for doing a binary classification. Okay, and such a structure is very interesting. First of all, as I said, there's no Barron plateau effect if we exploit such a structure. And what's also interesting is that the number of model parameters that we need to optimize scales logarithmic to the number of input qubits. And usually the number of qubits we need to use for encoding classical information is also logarithmic to the number of features that we have in the classical data. So when we look at the number of model parameters to the number of features that we have in the classical data, it's like a double logarithmic smaller number of parameters that we have to optimize. So it's like extremely compact model for machine learning. And this has like a shallow depth, and we train gates, and this only requires 1 qubit measurement. So we thought this is an excellent fit for near-term noisy intermediate scale quantum computing. So we did some benchmarking on this quantum circuit. We used so this was just a classical simulation of the quantum algorithm. We used 8 input qubits to train the circuit to do binary classification on MNIST data. Like we were hoping that a quantum circuit will distinguish 0 and 1, and also the quantum circuit could distinguish shorts and pants. So we tried these 2 different binary classification tasks. And the results were very promising, even though this is only like a numerical simulation. We saw a very good performance on a quantum computer. So for example, when we look at the MNIST data classification, we have all these bar graphs from 1 to 10. These are like 10 different ways to parameterize the quantum circuit. So we tried a variety of sets of models, and the number that you see on a bracket, like ranging from 12 to 51, they are the number of model parameters that we had to use to train those quantum circuits. So the number of parameters, again, they're only from 12 to 51. And despite having such a small number of free parameters, the classification test accuracies were very high. Like they are at least like 98%. However, if we compare that to like classical, like state-of-the-art CNN, of course that's not as good as the state-of-the-art classical CNN. But we have to keep in mind that classical CNN typically uses like hundred thousands of free parameters, up to even like millions of free parameters. So we thought maybe it's not a fair comparison to compare our like compact model to more complex CNN model. So we downgraded the classical CNN model so that the number of model parameters are comparable to the range of 12 to 51. So for example, we designed the classical CNN with 44 parameters. And this really, like, when we look at it from classical machine learning perspective, this doesn't really make sense. But just for the fair comparison, we downgraded classical CNN. And what was interesting to see is that when we downgrade classical CNN to have just a small number of parameters, the performance was actually lower than what we could achieve on a quantum computer with similar, with basically the same training condition. Okay, and we have observed something very similar for this fashion MNIST data as well. So this was very encouraging and promising result. So basically, if I just summarize this result in like one sentence, we observed higher accuracy on a quantum computer in the few parameter regime. So this happened only in this regime. And of course, it will be interesting to scale it up, but for now, we only observed such an advantage in the few parameter region. Okay, and then like before waiting for we have a quantum hardware with which we can really scale up this quantum circuit, we thought about how to like fully utilize such nice feature of this quantum CNN. And we thought maybe transfer learning would be a very natural place where we could apply this idea. So we tried classical to quantum transfer learning. So we pre-train a CNN. So this is classical CNN using like specific set of data. And then once we have this, then now this will serve as a base. And then now we train a quantum convolutional neural network for completely different task. So here, the classical CNN is trained to discriminate like this fashion MNIST image data set, and now we use that reference, and we basically truncate the some of the layers at the end, and then we basically attach quantum CNN to this classical CNN as as to fine-tune the model specific to the new data set. Okay, this is a very common idea that people often do in classical machine learning. And so we by simulation, we also compared classical to classical transfer learning and classical to quantum transfer learning. And we have tested this for doing a classification between 0 and 1, 2 and 3, and 8 and 9. And in all cases, basically, there are lots of bar graphs, but basically all these like bar graphs, they are obtained from this classical to quantum transfer learning, whereas the solid lines are obtained from classical to classical transfer learning. And these results were quite promising because they all support that it will be more beneficial to do classical to quantum transfer learning rather than purely classical transfer learning. All right, so these are all empirical studies, and we wanted to understand this from more foundational, like fundamental perspective. So we were asking this question: so what does a variational quantum classifier really do? And in the end, it's just doing what's known as quantum state discrimination. And maybe this terminology is not very familiar to many of you, but this is an idea that came out even before the birth of quantum computing. So people in like 1960s, 70s, and thought about how to design such a measurement that discriminates two different quantum states. And sorry about the broken equation, but basically this quantum state discrimination problem can be framed as some optimization problem. And in I think it was like 60s, Carl Hellstrom actually solved this optimization problem for the binary case. So in the binary case, we can write down the optimal solution analytically, and it's known as Hellstrom measurement. So in the binary case, we know the bound. We know how good we can do. It's known as Hellstrom bound. And what's interesting about this Hellstrom bound is that, in fact, given these two quantum states, rho 0 and rho 1, so these are the quantum states that encode two sets of classical data. One belongs to class 0, and second, the set of data that belongs to class 1. Okay, so rho 0 and rho 1, they represent like quantum encoding of the given classical training data set. And basically, what the theory that we can see from this quantum information theory is that once the state encoding is given, and then whatever we do on it, on a quantum circuit with a quantum computer, we can never increase this bound. This bound only decreases. Okay? And this is very important to understand from fundamental point of view. And so basically, variational quantum circuits that, whatever people say about it, it's all about that the training accuracy is completely determined by classical to quantum encoding method. And once that's given, variational quantum circuit simply tries to reach this bound. It tries to find the optimal set of measurement to reach that bound. That's it. So of course, from fundamental perspective, it's very important to think about how we go beyond this limit, and this only tells us about training error. So what about the test error? So there are many interesting questions that spring from this theoretical analysis. So we thought, okay, so one way to go beyond this limit is to train the map that's specific to the data set, because here all the variational quantum circuits that they train the same map for all the data sets. So we thought maybe we can think about training a map that's specific to training data set. Then perhaps we can avoid this bound, and that actually corresponds to a one-class classification. Okay. So in one-class classification, this is slightly different compared to binary classification. It's slightly more difficult than binary classification because the data set that we have for one-class classification, which aims to train the map that's specific to the data set, that does not have the label information. So this is a little bit more difficult problem than binary classification. And just to make this story short, the final story is that the quantum model uses again an exponentially smaller number of parameters compared to the usual classical models. Nevertheless, the quantum one-class classification performs comparably well to the well-known methods like kernel PCA, one-class SVM, and also deep convolutional autoencoder. Okay, so maybe I'm not sure if I'm running a little bit out of time, but finally, I wanted to say that, well, basically this everything that I talked about, this Hellstrom bound and so on, the theory of quantum state discrimination basically tells us that the general measurement in quantum mechanics, which is called positive operator valued measurement, POVM, can actually distinguish non-orthogonal states, okay? And this is indeed the foundational difference between quantum and classical when we do classification, okay? So we thought about designing a quantum circuit that directly implements an arbitrary POVM. And then we try to parameterize a quantum circuit that directly implements POVM, and we try to train that circuit to perform like multi-class classification that distinguishes non-orthogonal states. And maybe on the right-hand side is the main result. So we tried that on very simple iris data set to do like a 3-class classification. And the end of story is that the quantum multi-class classifier based on this POVM performed very well. All right, so I have listed a couple of open problems for near-term quantum machine learning. As I've already said before, variational quantum circuits or variational quantum algorithms, and also like non-adiabatic quantum annealing, they are very popular approaches for near-term quantum machine learning. But we need to be careful because we need more theory needed to make like strong claims about quantum advantage. And also we need to be able to avoid barren plateaus effect while retaining the quantum advantage. And also a lot of results are given under like empirical studies. So it's important to understand how quantum machine learning methods scale to large problem sizes. And as I've already indicated through this analysis with Hellstrom bound, quantum data preparation is a very important topic. For example, how to encode classical data efficiently as a quantum state. So this is really, really important topic. Okay, and I've mentioned something about improving the binary classification beyond the Hellstrom measurement. And finally, as all of you know very well, that we need to take care of shot noise and hardware noise. Okay, and that's it for my talk, and thank you very much.
Thank you for your wonderful presentation, despite of the incomplete material status. It was very helpful to understand how we should approach quantum machine learning.